All right, welcome to problem set 30. This is our last one. So that's exciting. We're almost all done. We're of course going to just start off with number 1 here. And it says determine the area enclosed by f of x and g of x if f of x equals x cubed and g of x equals x squared plus 2x. So of course, to figure out the area enclosed by that, we first want to look for any intersection points, right? So I'm going to set those two equal to each other to figure out when those are. So when they are equal, and then I'm just going to solve for x, and let's see. I think I'm going to move everything to one side, so it's just going to be x cubed minus x squared minus 2x equals 0. And I think I'll be able to factor this out. So I'm going to factor out that x so that this is in a form that we're more used to seeing. And then from here, I think I can factor that out. So that'll be an x, and then I believe that's going to be x minus 2 times x plus 1. Which means, let's see, and if I was to FOIL that back out, so let's just double check our work here. So if I double check that, that's going to be x squared plus 1x minus 2x minus 2, which then simplifies down to x squared minus x minus 2, which is exactly what we had there. So that factoring checks out, which means, so this all equals 0 when x equals 0, x equals negative 1, or x equals positive 2, which means that these two functions intersect, or they cross each other at these x values. Now, we need to figure out on each of those intervals, so in order from negative 1 to 0, and then from 0 to positive 2, we need to figure out which function is on top and which one is on bottom, and then we can set up our two integrals and evaluate. So in here, so it's from negative 1 to 0, so I'm going to plug in maybe a negative 1/2 to both of these functions. So f of negative 1/2, well, it's x cubed, so negative 1/2 cubed is going to be negative 1/8. And then g of negative 1/2, well, it's going to be x squared first, which is 1/4, plus 2x, that's going to be minus 2 over 1/2, because this is negative, right? So adding a negative, 2 divided by 2 is 1, so it's going to be negative 3/4. And I'm initially inclined to say that this is bigger, obviously, because 3/4 is bigger than 1/8. But because they're both negative, since this has a larger magnitude, it is actually smaller technically, right? Because it's going further into our negatives, which means that our f of x is on top. So top here is f of x. Bottom is g of x. Now I expect that those will flip for this next interval, but we can't be too sure until we try it. So let's plug in something along this interval, say 1. So f of 1 is just 1. G of 1 is going to be 1 plus 2, which is 3. Clearly the top here is g of x, and the bottom is f of x. So now we can set up those integrals. So this first integral is going to be from negative 1 to 0, and it's going to be f of x minus g of x. So it's going to be x cubed minus this. And then add our second integral, which is going to be from 0 to 2, because that's that second interval. It's going to be the opposite. It's going to be g of x minus f of x. And I am going to keep that in standard form, so it's going to be negative x cubed plus this. And now it's just a matter of evaluating. So let's see, so it's going to be 1/4 x to the 4th minus 1/3 x cubed minus, well, that would be 1/2 times 2x to the 2nd. So it's just going to be that. And that's from negative 1 to 0. And then plus Same deal in this case, except some of our signs flip around, right? And then from 0 to 2. And then we plug those in. Let's see, plugging in 0, I'm obviously going to get 0. And then we're going to subtract, plugging in that -1, plugging in -1 there. It's just going to be 1/4. -1 here, it's going to be -1/3, but we're subtracting that, so it's a plus. And then this is going to be -1. Okay, let's plug in that 2 over here now. Plug in a 2 here. 2 to the 4th is 16. So it's -16 over 4, which is -4. Plus 8/3 plus 4 minus plugging that 0, which is just going to all be 0. Now we want to distribute that negative. So it's going to be -1/4 minus 1/3 plus 1 plus, oh, let me see actually that these cancel, so I can just knock those out. Then plus 8/3, right? So now we just combine like terms. So let's see if I can easily combine this and that, so that's going to be 7/3. Combining 1 and -1/4 is going to be 3/4. This will probably be easiest done with a common denominator, so it's going to be 21/12. Nope, sorry. 28/12 plus 9/12, so it's going to be 37/12 or 3 1/12. Boom. Okay, I'm going to erase all of this now so we've got space for the next problems because I took up a lot of space with this. Yeah, let's take a look at number 2 now. Number 2 says determine the area of the region enclosed by these 3 equations. Okay, so again, we're going to look for all of our intersection points, and for problems like these, I really like to sketch it out because it helps me understand which one is on top and on bottom for certain stuff. You can obviously do things kind of the same way we did number 1. Oh, never mind, sorry, we're on this one, not this one. I scrolled down a little too far. Oops, just skipped right past number 2. But when we get to this one, we'll probably sketch it out. In this case, let's see, I want to turn them both into y equals equations. So y squared equals 12x, that's going to be y equals square root of 12x. X squared equals 12y, that's going to be y equals x squared over 12. And of course, we want to find those intersection points, so we want to set those equal to each other. I first see that they're both going to be equal when x equals 0, of course. So we'll keep that in mind as an intersection point. Let me just erase those up there so we don't get confused. Okay, so one intersection point is x equals 0. Setting these equal to each other now. Easiest thing to do here is just square both sides. So 12x equals x to the 4th over 144. Which gets us some big numbers, but it's going to be, I then move those over, so if I divide both sides by x and multiply by 144, that's clearly going to get 12 to the 3rd equals x to the 3rd, so x equals 12. So the region between these two functions is going to be between 0 and 12. Between x values of 0 and 12. So I need to figure out which one is on top, and I expect it'll be this one here just because of how I know those appear, because this is an x squared divided by 12, so it's going to be something akin to our typical parabola, right? But it's going to be just a little bit scaled differently because of that divided by 12. But this is going to look something like that, which would make it on top, so our area would be somewhere in there, right? If we say that this point is that 12. So using that, we can actually just put together that right there. If you want to double check that, of course, you can plug in a value on this interval like we did before for both of these and see which one is on top, but it should be the square root one. So it's going to be this one minus this one. So, give myself more space. And I'm going to write this, I'm going to write it like this. And then that's minus x squared over 12. And from here, we then just have to integrate, but it is a little bit tricky because we do have that square root there, don't we? And integrating a square root is not super easy. Just like glancing at it, right? So let's see. We could, no. I wonder if I could just distribute that 1/2. I believe I can, right? So if I have 12x all to the 1/2, that should be theoretically be the same as the square root of 12 times the square root of x. Doing that, obviously, I wouldn't have to, I could just integrate normally because this would just be a coefficient, right? I think that works. I think that works. That's what I'm going to do. And let's hope that that's correct. So going backwards then, so I'm going to rewrite that there. Going backwards, we just have to use that power rule. So it's going to be square root of 12 times x to the 1/2. So it's going to be, if I add 1 back to that, that's going to be x to the 3/2. And of course, we have to then divide by that, and then that's going to be times our square root of 12. So, and actually square root of 12, I can simplify a little bit to be 2 times the square root of 3. So this, so it'd be 2 times square root of 3 times 2 divided by 3, which would be 4 square root of 3 over 3. So I'll write it that way, 4 square root of 3 over 3, x to the 3/2, and then undo that power rule, so it's going to be minus, that's going to be x to the 3rd, and I'm going to divide by 3, so that's going to be 36. And then we of course have our bounds, and then we plug things in and evaluate, and I feel like I've made a mistake somehow, but I don't know how. I'll check my answer at the end. Oh, that's a really small 0. Why did I draw my 0 that small? Let's plug in these bounds. So if I have 12 to the 3/2, that's of course square root of 12 cubed, which, let's see, so that'll be square root of 12, which is 2 times the square root of 3, cubed times 4 times the square root of 3 over 3, right? Now, to simplify that a little bit further, I could turn that back into a 2 and then just have that extra 2 separately, which would make this actually to the 4th. So it'd be 2 square root of 3 to the 4th, which is going to get rid of that radical. So it becomes this. And so, of course, 2 to the 4th is 16. Square root of 3 to the 4th, well, it's going to be 3, and then that's squared, so it's going to be 9. So it's going to be 16 times 9. Whoa, that's a big number. It's not 196, is it? That feels, Hold on. It's 144. Okay, so that becomes 144 times 2 divided by 3. Which obviously, well, suppose we don't actually have to multiply that out because I could factor out the 3 there, so it becomes just 3 times 2 times 16, which is 6 times 16, which is, let's see, 64, 80, that would be 96. That makes sense. Okay. Okay, so this turns into a 96. Then we have to subtract this, so that's x, so it's 12 cubed divided by 36. And remember that I'm gonna just expand that so that I can get rid of some stuff, right? Because 36 is 12 divided by 3. So it's actually 12 times 12 divided by 3, but that's gonna be 4 times 12, which is just 48. So now, simplified that first bit. So I've got 96 minus 48, which is just 48, I believe. And that's after plugging in that 12 bound. Now if we plug in 0, it's all going to be 0, so it's minus 0, which makes that area 48. Now that feels wrong. I feel like I made a mistake somewhere. So give me one moment while I double check this. Oh, no, that's correct. Okay, cool. Cool, no mistakes here. I was just feeling really iffy about separating that out, but works out. Okay, now we take a look at number 3, which, again, we're going to look for those intersection points. And again, I would recommend sketching it out. So first I'm going to look for intersection points between y1 and y2. So it's going to be x minus 2 equals negative 2x plus 4. So of course 3x equals 6, x equals 2, okay. So x equals 2 is between those two. Let's try y2 and y3. So it's going to be negative 2x plus 4 equals 16 minus x over 4, which is the same as 4 minus x over 4. So now I've got, let's see. If I subtract that 4 from both sides, I'm going to get negative 2x equals negative x over 4. I'm going to multiply both sides by 4, so negative 8x equals negative x. Interesting. I feel like I've made a mistake. Maybe not. Okay. Which would then be, of course, that negative 7x equals 0, which would be x equals 0. So they intersect at x equals 0. And now, look for any intersection points between y1 and y3. Oops. Why is it not undoing? It always does this. Okay. So x equals 0. And now, between y1 and y3, so x minus 2 equals 4 minus x over 4. So x minus 6 equals negative x over 4. Multiply both sides by 4 again. We have 4x minus 24 equals negative x. 5x equals 24. I technically skipped a step, but I'm just moving that and that to the opposite sides. That's ugly. Why is that ugly? I made a point of making these problems not ugly. So why are they ugly? Did I make a mistake? Okay, well, x equals 24/5, which is 4 4/5. We will work with that, that's okay. I just feel like I've made an error somewhere. But I might have just messed up setting up this problem to begin with. So it's unfortunate. Now, for my sake, I'm going to sketch it out to get an idea of how these line up. So it's, of course, x minus 2, which means that if that's negative 2, 4, 6, yeah, should be fine. So this obviously has a y-intercept of -2, and I'll color code these really fast. So it's going to be right there. And of course that's just a slope of 1, so that's going to be 2, 4, 6, 8, 10. Okay, which means that if I go up 2, it's going to go over 2, and so on, of course. So that line looks something like that. Next up, we've got -2x plus 4, so there's a y-intercept at 0, 4, and it goes down 2 for every 1 over. So if I go over there, well, that makes sense, they intersect right here, okay? Then it's going to be right there and right there. And that line's going to look, oops, something like this. Okay. And then we graph that next one, which is the same as, we said that was the same as 4 minus x over 4. So there's a y-intercept of 4, just like that one. Oh, yeah, so they should intersect at that. Yeah, so these two intersect at x equals 0. And then let's see. So that means for every 4 x values I go over, it's going to go down 1. So we're going to go 1, 2, 3, 4, and it's going to come right here. And I think these should intersect at actually 4, not 4 4/5. Just based on this. So I think I just made an algebraic error somewhere. Because this makes the most sense. Okay. Which means that y3 is on top the whole time, but our bottom one switches at x equals 2. So we're going to have two integrals for this. So it's going to be from, let's see, from 0 to 2. It's going to be y3 minus y2. So it's going to be 4 minus x over 4 minus -2x plus 4, which cancels out those. And I can combine x over 4 and positive 2x, because that's going to be like that. So it's going to be -7x over 4. So that's pretty simple. And then add the next one. So it's going to be from 2 to 4. 2 to 4. And it's going to be y3 minus y1, because now that's the bottom one. So it's going to be 4 minus x over 4 minus x So it's going to be 6 minus 5/4 x. Okay, and now we integrate. So all of this now, oops, all of this is now, let's see, undoing that, that's going to be -7/4 times 1/2 x squared, so it's going to be -7/8 x squared from 0 to 2, plus, that's going to be 6x minus 5/8 x squared from 2 to 4. Right, and now plugging in a 2 here, that's going to be -7 times 4 over 8, which is of course just going to be -7 over 2. Plugging the 0, it's just -0. Plugging in our 4 over here, it's going to be 24 minus, let's see, so it's 5/8 times 16. So it's going to be 2 times 5, which is 10. And of course minus, putting that 2. So -12 minus negative 5/8 times 4, which is just 5/2. And now we combine, so that's of course just going to be 12 minus 10, which is 2. Negative 7/2 plus 5/2 is then negative 2/2, which is negative 1. So it's 2 minus 1. And our area is 1. Keep in mind it's entirely possible that I've made a mistake somewhere in there. So be careful and try to be vigilant to catch those. Don't just take everything I do at my word, because I do make plenty of mistakes myself. Number 4 uses some implicit differentiation. So we're given this equation here, and we want to find dy dx by taking the derivative. So of course, if I have x squared plus y squared equals 72y, taking the derivative, that's going to be 2x plus 2y dy dx equals 72 dy dx. Sorry. And then from there, we just have to solve for dy dx. So I'm going to put both my dy dx's on the same side. So it's going to be 2x equals 72 dy dx minus 2y dy dx. And then I'm going to factor out that dy dx. So it's going to look something like this. Okay, and now to get dy dx by itself, I just divide this off. So our dy dx is going to be 2x divided by this. I am going to cancel out those 2's, so it's just going to become x over 36 minus y, right? Because this would be 2x over 72 minus 2y. I can factor 2 out of all of those, and it becomes this. From there, they want us to find the equation of the line tangent to the graph at the point negative 6, 6. So of course, first step is find that slope. So our slope is going to be this, just with these values plugged in. So it's going to be 6 over 36 minus 6. Oh, sorry, that should be negative. Which is going to be negative 6 over 30, which is going to be negative 1/5. So our slope is negative 1/5. And again, I think personally, I find the easiest way to do these questions to be using point slope form. So it's going to be y minus that y value equals the slope times x minus that x value. And then that's done. Again, you can always put that into slope-intercept form, or the ugliest one in my opinion, standard form. But both of those take significantly more effort, whereas this is pretty straightforward, so I go with this. Number 5 says d is the distance from a point, x, y, on the line y equals 4x minus 3 to the origin. We want to write d squared as a function of x, and then we want to find the point on the line that's closest to origin, using that distance, of course. So I like to sketch this out to give me an idea of what I'm looking at. So my line is going to look something like that. So that's going to be that y value, and then origin is of course there. So any distance would be something like this, right? So that creates this triangle where the distance over is x. Of course, this is 0, 0. And then the height is whatever y is. Okay, and then this would be that distance d. Now, using my Pythagorean theorem, because that's a right triangle, d squared equals x squared plus y squared. And that seems difficult to work with until we realize that we have y in terms of x. So it's d squared equals x squared plus 4x minus 3 squared. And you probably can put it in the homework like that, but I am going to actually FOIL this out and then combine like terms. So that's going to be x squared plus 16x squared minus, let's see, that would be 12x, 24x plus 9. So d squared equals 17x squared minus 24x plus 9. Okay. Now we want to find the point on the line that is closest to origin, which means that we want to find the minimum distance. So since we have a function for a distance. So we've got d squared equals this. Of course, we know how to find our minimum. We do use the first derivative test to do that. So if I take the derivative of this, it's going to be 2d. So I'm forgetting how to write this right now, but it's essentially, I can essentially take the derivative of this and just cancel off those 2's. So it's going to be then 34x minus 24, and then divide everything by 2. And that should not be a d, I don't think. That should be a dx. But, so it's a capital D, just for sake of writing it. There should definitely be an extra d there. Sorry. If you'd like to, you could take the square root of all of this and then take the derivative, if that's easier for you to understand. This is a little bit of a shortcut that I understood, but I'm currently blanking on how exactly it works. So in terms of explanation, I'm not sure I can give a great one right now. But basically, it's going to get us this. So now we need to find when this equals 0, right, to find our critical points. So 17x minus 12 equals 0. That's going to be when x equals 12/17. And now we need to determine that that's a minimum. So, of course, create an interval. And now see when it is increasing and decreasing. So when that distance is increasing and decreasing. So I'm going to plug in a 0 for that. So if I plug in a 0, it's going to be negative 12, which makes this negative, which makes this decreasing. So it's decreasing up to x equals 12/17. And then from here, I'm going to plug in a 1. It's going to be 17 minus 12, which is 5, so it's positive. This is increasing. It's increasing from there, which means that this point is a minimum. Good. Which means that this line is closest to the origin when x equals 12/17. Now be careful. A lot of us, we plug in the x value and then we plug that back into the actual distance function to figure out what that minimum distance is. But we're asking for the point on the line that is closest. So we're not looking for that distance, we're looking for what point this is when x equals 12/17. So we have to plug in 12/17 to our y equals equation. So y equals 12/17 times 4 minus 3, which is 48/17 minus 3, which is going to be 2. And let's see if I subtract 34, that's going to be 14/17 minus 3, which is negative 3/17. So it's going to be 12/17, comma, negative 3/17. So it's going to be right about here probably. And that's it. On to our next question. We don't have too many for this one, there's only 8 total, but that 8th one takes a lot of time. But so number 6 says we want to figure out the original function, f of x, if the second derivative equals 0, the first derivative at this point equals 9, and the original function, when x equals 4, equals 24. So of course, for my second derivative to equal 0, I know that the only derivative of something that equals 0 is a constant, right? So taking that integral, I'm going to get that this function equals some constant, c. So if f prime of 4 equals 9, well, that means that our constant must be 9. So our derivative, our first derivative at any point is just going to be 9. Now, we're going to take the integral of this, right? So that's going to be f of x equals 9x plus some unknown constant. Now I can plug in what we know here. So f of 4 equals 24 equals 9 times 4 plus that constant. So 24 equals, that's going to be 36 plus c, which means that c must equal negative 12. which means our original function is 9x minus 12. It's a nice, straightforward one. Now number 7 returns to our, what's the word? Exponential growth function, which if you'll remember, looks something like this. Or if you'll remember, sometimes that k is written as an r, so a lot of people learn it and remember it as PERT, right? But so these are the same thing, of course. I'm going to be using the one with the k just because that's what I'm more used to at this point. So it says suppose some radioactive substance produces 3,000 counts per minute on a Geiger counter at a certain time, and only 600 counts per minute 4 days later. Assuming that the amount of radioactive substance is proportional to the number of counts per minute, what is the substance's half-life? Okay, so for this, because we don't know what certain time this is, we're going to consider the 3,000 counts per minute to be our P naught. So it's going to be P of t equals 3,000 e to the k if it's in, e to the kt. And we know that it's going to be, so it's going to be, we know that P of t is going to be 3,000 when t equals 0, of course, right? That makes sense because 3,000 equals 3,000 times 1. That makes sense. So now we want to solve for that k value. So we know that it's 600 counts per minute 4 days later. So I'm going to say it's 600 equals 3,000 e times to the power of k times 4, because t is 4 because it's 4 days later. And now I can solve for that k value. So I'm first going to divide off that 3,000. So I'm going to 600 divided by 3,000, which is 1/5. 1/5 equals e to the 4k. Take the natural log, so it's going to be natural log of 1/5 equals 4 times k, meaning that our k value is the natural log of 1/5 over 5. Sorry, over 4, because we're dividing off that 4. Now, using that, we can plug that back into that original function that we can now use for whatever we need to. So now we're looking for the half-life, so we're looking for what t equals when P of t is half of that original amount. So it's going to be, of course, 1,500, so it's going to be 1,500 equals 3,000 times this. When I divide off that 3,000, it's going to be 1/2 equals all of this. Now, of course, we're going to take that natural log again. So natural log of 1/2 equals all of that. And now we're just solving for t. And I don't believe that we need to simplify for this one, but feel free to plug it into a calculator once you're done. Because I think actually you do have to plug in a numeric answer onto the homework. But so of course I'm going to divide this off. So it's going to be 4 natural log of 1/2 divided by natural log of 1/5 equals t. So this is that substance's half-life. And if I plugged that in, I do want to see what that looks like numerically. So if I plug that into a calculator, let's see. And it's going to be a half-life of roughly 1 723,000 days. So a little under 2 days is the half-life there. Oops. Now for our very last question, though this one is time-consuming, is if f of x equals this here, so 1 over x squared minus 6x, we want to find all of this information. So first we want to find the y-intercept, so that's of course plugging in x equals 0. When x equals 0, if I plug in 0, it's going to be 0 minus 0, which of course makes this undefined, so there is no y-intercept. It does not cross the y-axis. Our axis of symmetry, well, that depends if this function is even or odd, or neither, right? So first I'm going to check to see if it's even, which would mean that this is the case. So if I plug in a negative x for that, so let's see, so f of negative x in this case is going to be 1 over still x squared, but then it's going to be plus a 6x, which is not equal to this original function, so it's not even. Let's see if it's odd, which would be this. So if I plug that in, when we did that already, a negative f of x, though, would be more like this, which also isn't equal to that, so it's not even and it's not odd, which means it's not symmetrical with respect to any axis. So it has no axis of symmetry. Now we want to find our relative minimums and maximums, which of course just means we have to take that, at least that first derivative. We also want to find inflection points and concavity, so we'll need to take the first and second derivatives. But before we do that, let's see if we can recognize any asymptotes. So let's see, is there a horizontal asymptote? Well, remember, a horizontal asymptote is dependent on the top power, the top highest power, and the bottom highest power. Of course, since this is higher than this, believe that means our asymptote is going to be approaching y equals 0. So our asymptote is the x-axis. Give me one moment just to double check that. Yep, okay. That is correct. It has a horizontal asymptote of the x-axis, so y equals 0. Let's check for vertical asymptotes, though, which is, of course, when the function is undefined and it's not a jump or a hole. So it's not going to be a jump because this isn't a piecewise function or an absolute value or anything. We know that x can't equal 0 because that would make the denominator equal to 0. But I also want to see if there's any other possibilities where that would be equal to 0. And that would mean x squared equals 6x. So x equals 6, because I have to divide off those x's. Okay, so x can't equal 0, and it can't equal 6, because both of those make the function undefined. Now, are those holes, or are they asymptotes? Well, for it to be a hole, we have to be able to factor it out of the top to be able to get rid of that discontinuity, essentially. Which obviously, since our top is just 1, we can't do, which makes both of these asymptotes. So I have an asymptote at x equals 0 and at x equals 6. Now, let's go about taking those derivatives, because we need that for the rest of the questions. So, of course, we're going to use quotient rule. So that first derivative, let's see if we remember quotient rule, it's low d high minus high d low over low low. So we're going to take x squared, okay, so it's going to be x squared minus 6x times the derivative of the top term, which is, well, the derivative of 1 is 0, so it actually gets rid of that term, so I'm just going to erase that there, minus the high term, which is 1, times the derivative of the low term, all over the bottom squared. So that's going to be, yeesh, okay. Let's see if we can work with this at all. So it's going to be, of course, negative 2x plus 6. But I don't need to do that. I'm going to factor out the 2. It's going to be this. And I wonder, so of course, that squared would be x squared minus 6x times x squared minus 6x. And of course, you don't need to simplify it as much as I am. Excuse me. But I like to have it as simplified as possible, just to make it a little bit easier on ourselves. And I think I can cancel something out, because I think I can factor out that x. And it becomes this. And of course that will cancel out with that. So I'm going to cancel that out. So now I've just got a -2 up top. And this left. So -2 over this. Okay. And actually, could even factor that a little bit more. It could be an x squared times x minus 6. Okay, so there's our first derivative. Now taking the second derivative, we need to use that quotient rule again, which is part of why I like to simplify at least that first derivative as much as possible, just so that it's not as ugly and complicated to take the next derivative with. I am going to distribute that out actually, just so it's a little bit easier to take that derivative. Okay, so now it is low d high. The derivative of -2 is 0, so that low d high term disappears, minus high, so it's going to be plus 2, d low, so it's going to be 3x squared minus 12x over low, low. Now from there, let's see, can I do any more factoring? Because it would be really nice if I could. So again, I'm just going to expand that a little bit. And I see I can factor out an x from that top. And so I'm going to also factor out an x from the bottom, so I can cancel that. So it's going to be x squared minus 6x. And then that. Okay. Then that x is going to cancel off, so it's going to be 2. And I can actually factor out that 3, so it's going to be 6x minus 4. And I did sort of skip a step there. So I canceled out one of these x's, right? So this became 3x minus 12. And then I also factored out the 3, so it's 3 times 2. Take out the 3 there, and take out the 3 there. And now, left with all that down there, and I can factor out more x's, so it's going to be x minus 6. Then I can factor out another x squared, x minus 6, so it's going to be x cubed times x minus 6 squared. And again, there's not a super huge reason that you need to factor it out that much. It just, I find that it helps me personally, especially with recognizing any zeros and discontinuities. So now we want to find our relative minimums and maximums. So we need to find our critical points, which this can never equal 0 because, of course, we're always going to have a constant up top, and any zeros down here would just make it undefined, right? So we don't actually have any critical points, but remember, we have to remember this discontinuities. X cannot equal 0 or 6, right? And we see that that's the same thing here. Okay, so x can't equal 0 or 6. Let's see, for this though, we have an inflection point at x equals 4, and then again, x can't equal 0 and x can't equal 6. Okay, so in terms of relative minimums and maximums, I don't think we'll have any. So I'm going to put none, right, because there are no critical points. We just have asymptotes and an inflection point. So shouldn't be any relative minimums or maximums. We do have an inflection point at x equals 4, and now we just need to figure out our intervals of increase, decrease, and concavity. So we'll do negative infinity up to 0, 0 to 4, 4 to 6, and 6 to infinity. Now, I want to find my intervals of increase, decrease first. So I'm going to take that first derivative, I'm going to plug in maybe a -1, right? Because I just want to plug in something on this interval to see if it's positive or negative. So it's going to be -2, so it's a negative up top. And it's going to be 1 times -7, so that's a negative on the bottom, which is positive. So this is increasing. Plug in maybe a +1 now, and I've got -2 over 1 times -5, so that's also positive, so that's increasing. Plug in a 5, and I'm going to get -2 over 25 times -1. Negatives cancel out, and that's still increasing. And then if I plug in maybe a 7, I'm going to get -2 over 49 times 1, which that's just negative on top, so it's decreasing there. Okay, so our interval of decrease, and because it's interval of decrease and not concavity, I would ordinarily include that bound, but we want to think about the fact that it is outside of our domain, which means that cannot actually be inclusive, so it will remain not included. So it'll be 6 to positive infinity, non-inclusive, is our interval of decrease. Now we want to test for concavity, so I'm going to do the same thing, but with my second derivative. So I'm going to plug in a -1, and that's going to be 6 times -1 minus 4, which is negative, and then it's going to be -1 on the bottom times a positive. Those cancel out. It's positive, which means it's concave up. Plug in a +1, and I'm going to get that 6 times a negative again. But now that's a positive, and that's a positive, so it's negative, which means this is concave down. Plug in a 5, and I'm going to get positive and positive on top, and positive on bottom. So it's concave up again. Let's plug in a 7. That's going to be 6 times positive over positive and positive, and it is concave up again. So now, remember that 0 and 6 are outside of our domain, but also intervals of concavity are always non-inclusive anyway. So it's going to be concave up from -infinity to 0, union 4 to 6, union 6 to infinity. And the reason I did not combine these intervals is because it's because those weren't critical points. This is just simply outside of our domain, which means we can't include it in any intervals. So keep that union there. And that's it. That's all we have left for this homework. And again, this is our last one for the class, which is awesome. So we are all done. Good luck on finals, everybody. If you haven't checked it out already, I did do a video already, and that should already be posted, with a review for the final, and hopefully that's helpful as well. Feel free to check that out. It should be in the same playlist. And yeah, I hope this was helpful. Thank you for watching.